So the next talk is going to be kind of in that space, but it is slightly different with scope of looking at optical transceivers and how do those would actually you can switch the slides to the next one. How those fare when they're exposed to radiation. And now think about this: we buy all this equipment. We believe it will work well, but nobody is actually doing any extended testing on some of those transceivers and to see how they will behave if they are under adverse conditions. So without further ado, we'll have the next talk.
Okay. Hi, everyone. I'll reintroduce myself if you're new. My name is Sean Klein. I'm a sophomore at Purdue studying electrical engineering. I'm here representing my mentor, Dr. Peter Bermel. This was work I did my second semester freshman year under Dr. Bermel. And basically, we are trying to qualify a commercial microelectronic, for example, an optical transceiver for satellite use. So starting off with the bottom line up front, or the purpose of this research, we're trying to enable the next generation of satellites by building radiation-resilient microelectronics to improve capability. Now, I know satellites might be a little bit far from what you guys do here on Earth, but there's still some considerations we have to be mindful of, irrespective of that. And so often when I'm going to pivot this more so for satellites, but I'm going to include some of the industry stuff. Often when we're building satellites, we face a critical trade-off between capability of our satellites and the size, weight, and power of our microelectronics. So we want to make sure that there's a balancing act that we're doing. And the goal of my research was trying to balance that and then make sure that we have the utmost capability on our satellites while still preserving that microelectronic capability. So starting off with a little bit of a background on electrical communication. So historically, engineers have used copper wiring to transmit signals. The problem with copper wiring is it's very susceptible to electromagnetic radiation. Heavy ions and high energy photons can affect it. And you can see an example of such on the right here. And so that's a plot of two different types of copper, their resistivity over neutron fluence. So we could see that there's a nonlinear increase in resistivity as neutron fluence increases. And that could present some issues if we have a copper wire on board a spacecraft being exposed to those neutrons in geospatial orbit or other types of orbit. So moving on to photonic communications. So photonic communication uses light as the medium for relaying data instead of electrical currents. And it's faster than electrical signals, as I'm sure we all know. And it could be more energy efficient over long distances. The other benefit of photonic communications is that it can be more robust against certain types of radiation as opposed to others. And we can see here on the right is an example of such a photonic device. And this is the specific optical transceiver that we used. So moving on to radiation hardening and its use. So we've identified that photonic devices present an alternative to the historical copper wiring that engineers have used, but how would we protect it in space? So we have kind of three different types of effects that we're looking out for. So TID, total ionizing dose, which is the total ionizing dose required to permanently cause current leakage or voltage shifts in your microelectronic, or DD, displacement dose, which is the total energy needed to knock an atom off its lattice structure. You're going to therefore degrade the microelectronic's lifetime. Or SEE, or single event effects, which specifically working at single event transients. And those are potentially effects that flip a 0 from a 1, or flip a 1 to a 0 or 0 to a 1. And as you can imagine, if you have data that's being transmitted, you really wouldn't want it to be corrupted in space where you don't really have the fallback mechanisms to manage it. And literature has determined that a 2 millimeter multi-layer shield can cut your total dose by over 50% while staying within mass budgets for flight missions. But the novelty of this research is applying that methodology, that shielding methodology, to a commercial off-the-shelf transceiver. And if I didn't highlight it before, we're looking at a commercial microelectronic because often when you're building or qualifying these microelectronics for spaceflight, you have to invest a lot of upfront costs in R&D to make sure it's going to be designed specifically for the mission. But we want to implement as a framework that can just be applied to any optical transceiver off the shelf and then see what happens from there. You could see here an example of radiation hardening. So, paper is getting alpha particles is getting attenuated by paper, beta particles are getting partially attenuated by aluminum, while gamma particles are getting partially attenuated by lead. You can apply the same methods for other materials, and you can see how attenuation works with those. Now, going back to the bottom line up front, so we've identified that photonics present an alternative methodology for data transmission. We're now going to go into how the shielding framework is built and how we apply that knowledge for the qualification. So going into some of the constraints I identified for modeling. So every gram matters on launch. So we want to make sure we're optimizing the thickness to minimize the mass. So we could get a very thick lead shield into space, I'm sure, but we don't want to overcompensate more so than we need to. So we want to make sure we're minimizing the total mass. Thermally, conductive layers, we want to prevent within 1 watt of overheating, so there's no atmosphere to dissipate heat in space. So we want to make sure that we're spreading the heat pretty evenly. We don't want to overheat the microelectronic. And then structurally, different materials degrade and react in space differently. So for example, polymers tend to outgas, meaning the VOCs inside them bubble out, and that's going to cause some structural degradation. So what you can do is you can encapsulate them in other different materials to prevent that. Moving into the layered shielding design that I utilized for my modeling work. So this is pretty standard. So it uses a high Z layer, which could be made of tungsten or tantalum for gamma or proton attenuation, and a low Z layer of HDPE or boron-doped polyethylene for neutron moderation. And the idea being, so you can think of primary and secondary radiation effects as the following. So if you have a glass ball, your primary effect is it hitting the ground versus the secondary effect, it's shattering. So even though you're preventing some of these primary effects, we still want to make sure we're compensating for some of the secondary effects that could occur. Going into the modeling procedure, I use transport of ions in matter. It's a older software developed to simulate proton attenuation. And we identified some shielding candidates from that could improve upon the transceiver's baseline effectiveness. And you can see here on the right is the mechanical specifications of the FinSAR SFP that we used in this research. And here is going back to our goal. So we have identified there is a procedure that we can use to shield, but now we're going to go into how the candidates work and the different candidates that we have identified as potentially usable. So to determine the simulation procedure, I used 1,000 ion trajectories per candidate, trying to balance both statistical significance and the time it takes to run the simulation. And we chose a penetration depth of 1.5 to 2.5 millimeters. That was the region where most of the energy deposition occurred based off of the experience I had modeling. And then we wanted to compare the shielding candidates under realistic radiation conditions. Those were determined to be between 10 megaelectron volts and 50 megaelectron volts. So we wanted to be representative, I believe, of low Earth orbit. And so we could see the output from our baseline, basically. So you could see that on this guy is like the protons, and it's seeing how far it penetrates through these different materials. So I identified that the optical transceiver was likely encased in a zinc aluminum alloy, and then it had a polymer underneath that. So at a total width of 3.3 millimeters, it was able to effectively attenuate a lot of these protons, but theoretically we could improve upon that baseline, decrease the total width of the optical transceiver, and maybe use less mass in total. So that's what I'll go into now. So an example of such would be HDPE, tungsten HDPE, with an areal mass of approximately 0.721 grams per centimeter squared, a cost of materials of over 0.40 cents per centimeter squared, a thermal conduction approximation of 0.61 watts per meter Kelvin. And we can see here that there was pretty effective attenuation of these protons, and we even improved upon the original depth to decrease the total width. Going into another exotic material, boron-doped polyethylene, tantalum boron-doped polyethylene, with an areal mass of approximately 0.7101 grams per centimeter squared, a cost of materials of over $1 per centimeter squared, and a thermal conduction approximation of 0.46 watts per meter Kelvin. So this did not as effectively attenuate some of these protons, but we did improve upon, actually it was higher cost and we didn't improve upon the baseline. So this would we've identified that this candidate is maybe not something we're going to proceed with. Then moving to the next one, aluminum tungsten polyethylene graded Z stack with an areal mass of approximately 0.713 grams per centimeter squared, a cost of materials of 40 cents per centimeter squared, and a thermal conduction approximation of 0.87 watts per meter Kelvin. So here we've improved upon the thermal conduction from the baseline in addition to improving upon the total width. That would suggest that maybe this is an attractive candidate that we can continue to move forward with for the optical transceiver. Now going into tungsten-loaded silicon composite and then HDPE. So this is a more exotic material with an areal mass approximation of 0.44 grams per centimeter squared, and it's not sold commercially because it's an exotic material. It can only be made in a lab. And then a thermal conduction approximation of 0.47 watts per meter Kelvin. And we can see here that, you know, it's the smallest shield by far, but it's not entirely improving in some of the metrics. So this may not be something we're going to proceed with as we continue the modeling. So I want to try to bring in some experimental validation. So you're hearing these numbers, or at least the attenuation, and we tried to compare it to established NIST standards, and we found that there was a strong agreement across the energy spectrum, and so meaning that our projected range for attenuation versus the proton energy were pretty aligned. That's going to probably validate some of our results, not completely, but to some extent. And then I want to move back towards our mission. You know, we're trying to establish criteria to build the next generation of satellites radiation resilient microelectronics. And so we've identified some shielding candidates. Now I'm going to go into how we can validate them experimentally. So our test environment is going to be the Purdue subcritical pile. So it uses plutonium beryllium rods to generate neutrons for testing. And semiconductor devices, especially memories, can be sensitive to neutrons. And although the flux is generally low on Earth, in orbit the flux is much higher. So we want to make sure that we're simulating those conditions on Earth. The select small form pluggable SFP was chosen because it combines both memory, logic, and untested functionality that is commercially relevant, as I'm sure you guys would feel that way. And here is an example, or here's the image of the Purdue subcritical pile that we're going to use. So moving on to the test setup. So we're going to use a single transceiver testing using a loopback module, and that's going to be for self-communication. A bit error rate tester is going to generate the test pattern. It's going to measure the data for bit errors, obviously. And then the SFP is going to be linked to the BERT via an extender cable with the BERT placed outside the radiation zone. That way we know that any radiation effects we're seeing is not because the transceiver and the BERT is within the subcritical pile. We're trying to isolate the two. And then the loopback module is closing that path, isolating the radiation effects to the transceiver only. And then some of the requirements we have for testing. We want to make sure that the transceiver is moved across various locations in the subcritical pile. And then we're going to measure some of the system level behaviors such as bit error rates and error bursts under the radiation. We're trying to find degradation thresholds. So, if we're noticing that the transceiver really starts to fail under this specified amount, that's suggestive that, depending on the orbit we're in, we have to shield it more or shield it less. That's going to inform our modeling behavior and how we're building those models. And continuing with the connection to modeling, we want to convert these transceiver positions into estimated neutron flux levels, and we want to use maybe more advanced software that you've seen before. So Geon 4 is developed by CERN. It models a little bit more of the neutron effects than TRIM is able to accomplish. And then we're going to try to compare the bit error rates under these different neutron fluence levels that we've identified in the subcritical pile. And then we're going to use some of these discrepancies to refine the model thresholds and device parameters for the upcoming exposures. So ideally, we're creating a loopback of we have the experimental results. How does that inform the modeling? How does the modeling then inform our next experiment? And then we're going to continue to refine the model so that if you guys, for example, are trying to qualify your microelectronic, not necessarily for space flight, but anything that might be even low Earth orbit, if you have an aircraft, it's still going to be relevant to that. And the question becomes is how are you qualifying it for that? And so some of the implications in future work. So we know that graded Z structures are going to outperform aluminum. That's pretty established in the literature, but we were able to improve upon the transceiver's baseline materials. And we're going to do some further experimental testing of these exotic materials to see if they hold up under real-life radiation conditions. And then hopefully we're going to develop a deeper understanding of the trade-offs involved in selecting some of these materials. And you can see here on the right, this is an overview of the different candidates and their associated metrics. So we're trying to basically create a decision matrix from which, if you're trying to design a transceiver and you're trying to balance the capability, what specific metrics are you trying to optimize for? So is it size, is it weight, is it power, or is it more? And then kind of understanding like what the outcome is going to be in the real world. And here's my contact information. Thank you very much for your time.
All right, any questions? I'm curious, how many of you are looking at your equipment and kind of thinking through what's going to happen if, let's say, there's some adversarial conditions like, for example, well, you know what, I'm going to stop here and I'll see people that are interested in this topic here on the side. I just don't want to like kind of bring that up, but anyway, yeah, go ahead.
That's an interesting topic. I always wondered how this was all done up in the atmosphere, high up with all these low Earth satellites and things like that. So it's very, very interesting for me as a newbie. I'm a software guy, nothing to do with any of this. But I have a question. What are the failure mechanics of some of these materials you're talking about? And that's an important aspect for material science, mechanical, thermal, other properties. So what's the failure mechanics? Is there any work there in any of the stuff that you're researching?
Absolutely. So I'm not the most qualified to answer because it's a lot of radiation physics, but it's about when you have a neutron hit for example, the binary that's stored in the memory, how is it going to affect that? So I would say that, and this is drawing from memory, if you have you can think of an EMP. It's a very simple understanding, right? So if you have an electromagnetic pulse, so if you have electricity passing through, you could short something. I mean, that's just a very simple example, right? Some of the radiation physics is a little bit more complex, so it's a little bit hard to exactly express to you unless I have a specific example. But you can kind of think of it as like, okay, well, if you have a particle that's, for example, an electron that hits a circuit, right, you're going to induce a current. So if you have something in space that can only tolerate a certain current threshold, and you're inducing way above that, you're going to destroy the mechanics of it. So I think that's a pretty easy to understand, I hope. Does that answer your question? Oh, of the specific shielding. Oh, understood. So it depends. Again, it depends on the specific application. So for example, the failure mechanism of polymers in space are that they're going to outgas. So I mentioned that the VOCs. But radiation-wise, I'm not familiar exactly how a material, for example, boron-doped polyethylene, would specifically be degraded, if that answers your question, outside of some of the very clear thinking, okay, no atmosphere, so things are going to bubble out. That's easy for me to understand. Some of the more complex I don't have an answer for. I'm sorry.